This video looks at an exam question on correlation. So looking at the question, we have three airport manager trainees, Ryan, Sunil and Tim, and they're instructed to select a random sample of 12 suitcases, and the idea is to measure the volume and the weight and compare them and see if there's any correlation between volume and weight. Now obviously you would assume there would be, wouldn't you? So it's important to bear that in mind. This is the results. Ryan obtained a product moment correlation coefficient, an R value of minus 0.843, and Sunil obtained a value of plus 0.007. We're being asked to explain why neither of these two values are likely to be correct. So all this question's doing really is it's testing your understanding of the product moment correlation coefficient. You should know that the correlation coefficient runs between -1 and 1, -1 being a perfect negative correlation, which in the context of this question would mean that as the volume increases, the weight would decrease, and 1 at the other extreme being a perfect positive correlation, meaning that as the volume increases, the weight also increases. We see here that Ryan's product moment correlation coefficient of minus 0.843 is quite a strong negative correlation, implying that as the volume increases, the weight decreases, which doesn't seem very likely, does it? And Sunil's is practically zero, meaning there's no correlation between volume and weight, or very, very little. So for this reason, both of them are unlikely to be correct. In terms of answering the exam question, you need to show that you understand what these mean. So you would write that this is a strong negative correlation. You need to show that you understand what this one means, that it means that there's a very, very, very small positive correlation, practically zero, meaning there's practically no correlation. And then put them both in context of the question. They're unlikely to be correct because we would expect, as the volume increases, for the weight to increase. Have a look at the mark scheme, and you can see here that they're both B marks, and you can get them just by showing that you understand each of them. And you can see there's a bit of leniency over exactly how you describe it. I would like this point to be made, although you can see here it wasn't essential, but I think linking in the expectation that as weight would increase as volume increases, I think is quite an important one, and sometimes it's necessary in these type of questions, so I would certainly get in the habit of doing that as well. Okay, for the second part of the question, we have a supervisor, an experienced supervisor, Peggy, who has done the experiment herself. She's got a product moment correlation coefficient of 0.612, which seems a bit more likely, doesn't it? Ryan and Sunil each claim that Peggy's value is different from their values because she'd measured the volumes in cubic feet and the weight in pounds, whereas they had measured the volume in cubic meters and the weight in kilograms. Tim also claimed that Peggy's value was almost exactly half his calculated value because she had used a sample of 6, whereas he used one of 12. So here's the mark scheme here, and you can see there's just again 2 B marks, one for understanding that the units are insignificant. It doesn't matter whether we measure in cubic feet and pounds or in cubic meters and kilograms, we get the same result. The same product moment correlation coefficient. And similarly, the sample size doesn't affect the product moment correlation coefficient either. So we should get, And the other point you could make, although it's not essential for picking up the mark, is that actually doubling 0.612, as suggested, would be greater than 1, which is impossible, because it has to lie between -1 and 1. But just to say that it isn't affected by sample size would be enough for that B mark. So part C, Quentin recorded the volumes and weights of 8 suitcases, and these were the results. You are now being asked to calculate the value of R between the two variables, between V and W, and then to interpret your value in the context of the question. To do this, we need to enter the values in a graphic display calculator. You need to be in statistics mode. So get into there. We then need list 1 and list 2. In list 1, we put the volumes, so I'll just do maybe 3 for you just to illustrate. So the first one was 28.1. Second one was 19.7. And then the third one was 46.4. Then put the weights in here. So the first one was 14.9. Then 12.1. And 21.1. And actually, just looking at the numbers here, you can see that the biggest one has the biggest and the biggest volume. It's got the biggest weight, the smallest volume, the smallest weight, and the middle one there. Once you've done that, we need to make a calculation. It's actually a regression we want, but we'll just check to make sure everything's set up right. We want two variables. We want our first variable in list 1, our second variable in list 2, and the frequency needs to be 1 because we're not multiplying any of those. We've put each individual value in. We want that as 1. So that's set up correctly. If any of these aren't set up correctly, you would highlight them and change them. So if that wasn't in a list, you would need it to be similarly there. And this one here for the frequency, if you wanted a list to multiply any of these, you would do so, but we don't. We just want 1. But that's all fine. We then press F3 for regression. X we want. And there's our regression equation, and we get an R value, quite a good one for that one, of nearly 1, don't we, for that one. If you were doing a regression line, a plus bx, y equals a plus bx, you would use these for your equation of the regression line. But we'll look at a question involving that and interpreting regression lines later on in a different video. So all you need to do is copy down the R value, and then once you've got that R value, interpret it in the context of the question. Obviously the R value we got by just looking at these first 3 there gives a very, very strong positive correlation. What I'd like you to do now is to put all these values in and find out the real R value for all of the data and interpret that in the context of the question. Don't forget not only to say what type of correlation it is, positive, strong, moderate, positive. Use the word positive or negative, use the word correlation and comment on the level of it, but also relate it to the volume and weight and say what that means. Okay, I'll show you the mark scheme. Hopefully you've got a correlation between 0.5 and 0.6, which is what's required here for the marks. So the correct correlation value for the first 3 marks, and then for these 2 marks here, you need to use the words positive correlation, link it to the volumes and weights, and some way of quantifying what type of positive correlation. But you can see there you've got quite a lot of scope in terms of what you can use. Weak, some, moderate are all fine.